going to try to set the volume here. So I'm going to try to set the volume, and so I just want to make sure everybody in the back, can you kind of hear what I'm saying? It's all good? More up, more? Okay, it's good. Thumbs up or volume up? Thumbs up. Okay, cool. And just come find me, if it's quieter later on, just come find me or Michael or Chris, and then we'll fix it for you, okay? And so, all right, so thanks so much everyone for coming. It was exactly almost 7 years ago to the day that we started Science on Tap here at Blondies. And so, yeah, this is, I guess, our 8th season, so it's really exciting. So I'd like to make a big round of applause, and let's thank Blondies for putting up with us every month. Yeah, thank you to everyone. Be sure to check your survey as well, okay? And so we've been doing this every month when school's in session at HSU, so September through December and February through May every year. And we have a different scientist presenting something. And let's see, this is December, so next Science on Tap will be in February. In February will be John Steele. Maybe some of you know who John Steele is. He's in the biology department at Humboldt State, and he studies the gene editing tool CRISPR, which is a very hot topic right now. And so that'll be on February 6th, because we do the first Wednesday of every month, okay? So put it on your calendars. We have a Facebook page. That's our primary mode of communicating our events, so you can follow us on Facebook there. But for tonight, super excited to have our excellent presenter, Michael Furniss. And to introduce Michael, I'm going to turn it over to Chris Harmon, who's my co-host here. And we're both mutual co-hosts. And I'll turn it over to Chris from chemistry to introduce Michael. So thanks again for coming, everybody. This is awesome.
Let's give it a hand for Stevie Hoyle. As he said, he created this event 8 years ago, and I think it's done wonderful things for the community. So as Stevie said, my name is Chris Harmon. I'm a professor in the chemistry department, where I do research in climate change and atmospheric chemistry. So it is my pleasure to introduce Michael tonight and be a part of this talk. Michael did his undergraduate and graduate degrees at UC Berkeley, a place that's very near and dear to my heart. He currently serves as the advisory chair to the, I'm going to get this wrong, the Redwood Community Forest something advisory board. I've got all those acronyms. I took notes here terribly. Michael is also a hydrologist and climate adaptation scientist. He's retired from the U.S. Forest Service and Redwood Science Labs in Arcata. But since retiring, he has consulted, developed curricula, and taught nationally and internationally for about a decade. He has consulted in 16 different countries. Most recently, he's come back from the Congo, where he was there for a few weeks, working with the United States government and the local governments there. Most notably, he also spent some time in Vietnam. If you're not Facebook friends with Michael, I would really suggest doing that. He posts the best stuff. In fact, I'm usually late to my classes because I'm looking at all of his posts from countries like this. And Michael has also been a lecturer at HSU in engineering and forestry. So, without further ado, I'm going to hand it over to Michael Furniss. Let's give him a warm welcome.
Thank you, Chris. I have to say, HSU has the coolest professors.
Yay.
And so hats off to
Is that a climate joke?
Stevie Hall in the physics department and Chris Harmon in the chemistry department for this innovative science with beer. Yeah.
Beers with beers. Or wine.
So I've done a lot of teaching in climate change, and most of my lectures are unrelenting bummers. And you go on and you keep describing it. It's like, actually, it's worse than you thought. And the answer, here's this impact you haven't thought of. And it's worse than we thought, and it's getting worse faster than we thought. And it's really, and you watch the faces kind of drop and the despair build, and but there's this thing I've been noticing for a number of years that I wanted to sort of put the story together. And we seem to be kind of a climate refuge here. And there's some flies in the ointment, for sure. And I don't really have a great rosy story for you, because I think we all think globally now. And far be it from me to suggest that climate change is not something that we need to be terribly concerned about and take action on. And in fact, it's really in the news lately with the release of the 4th USA assessment. The 24th Committee of Parties is going on right now in Poland, the UN Triple C group that meets every year about climate change. That's happening now in Poland. And there's a bunch of media hype about all of this stuff. So this is timely. And this really is a serious and dire and existential threat. It's slow, but it's really inexorable as the greenhouse gases keep increasing. And so the degree to which this is a refuge here is kind of a relative thing. It's like, yeah, I got hit by a truck, but at least I didn't get hit by a meteorite.
Yeah.
Or, yeah, I got the flu, but at least I didn't get the bubonic plague. So it's not like everything's rosy and we're just completely okay here. We're not. But I've noticed that if you look at this area and the west coast, sort of San Francisco north through Washington, although there are some special things about our area, it's basically, it is a climate refuge.
It's going to be, going to happen now.
And I'm going to try and develop that story for you. And so here's basic climate science 101. It's warming. In the last 250 years, the land has warmed about 1.5 degrees centigrade. You know, that's not a lot, but we see the evidence of it basically everywhere. And heat and temperature are determinative for so many things, pretty much everything physical and biological. And the evidence of this rapid warming is just everywhere. And the natural climate cycle for the past million years, they consist of long periods of glaciation with short interglacial warm periods. And we're now in one of those warm periods.
Yeah, the mic.
Your mic, Jack.
Hold on one second.
Yeah.
There you go. There you go.
Yeah.
Yeah. That's better. Yep.
The physicist does a roadie here.
I'm on a band, so it's okay.
So it's one of those warm periods now, one of those relatively rare warm periods, and we don't expect the natural cycles at this point to contribute significantly to further warming. And it's us. So the humans have taken over. The human-caused increase in CO2 in the last 2 centuries has led to this 1.5 degree rise in temperatures, in land temperatures. And we can expect that CO2 increases from human burning of fossil fuels will increase the global average temperature another 1.5 degrees or more in the next 50 to 100 years. And we're sure this is now unequivocal and has been since kind of the mid to late 90s. And it's not the sun, it's not volcanoes, it's not cosmic rays, it's not natural. And there are multiple lines of evidence that show this, multiple independent lines of evidence that show this to be true. Okay? That one's not, that's not working as well.
How about now?
Hello, okay?
Is that okay?
It's good.
Kiss it.
Yeah.
All right. Thank you. Sorry about that.
Okay.
It's pretty smooth.
So we're sure about that, and it's bad. And it's not really that much yet. You can see the evidence everywhere, but it's a relatively small change that we've seen so far. But what's bad about it is the trend and where it's going. And we can see where it's going. And that's really cool. Although cool might not be the right word to use. And it's going to get worse and worse, and that's also unequivocal. And it's going to be worse for our kids, and it'll be worse for their kids, and it'll be worse for their kids. And we can fix it. There's reasons to be hopeful. And there's some very good reasons to be hopeful, and good reasons to be hopeful about our area in terms of adapting to the changes that we will see here. I shouldn't have to do this, but I wanted to
This is just the A's.
There's this denial industry that's gotten going. So if you had $33 trillion worth of assets, and a lot of people in the world were telling you you shouldn't dig them up and sell them, you might be motivated to do whatever you could to try to counter that idea. And that's what's happened. And it's something to perceive. I mean, we have a whole political party in the US that if you're a good member of it, you have to deny the science, which is as good as it ever gets, really. So it's an amazing thing. The state of California put this list together of the organizations, the scientific organizations. That is an organization that only has their reputation. That's all they have. That's why they exist. That hold that climate change has been caused by human action. I'm not going to read all these, but you can pick off your favorite one. American Meteorological Society. Yeah, what do they know? And here's another list of the American Society of Civil Engineers, Ecological Society of America, Geological Society of Australia. The list goes on and on. I'll note that the American Geophysical Union, Jay, is also on this list, of course, as the Society of American Foresters, the American Medical Association, the National Academy of Sciences of Armenia, on and on and on. Including the Zimbabwe Academy of Sciences.
Nice.
So if you're having a nice discussion with somebody who's denying climate change, you might ask them if they have any reputable scientific organizations who agree with them. And you'll hear crickets.
My brother-in-law.
And Fox News doesn't count. And so what happens, you don't actually need to propose an alternative theory here. You just need to
the Heartland Institute?
The Heartland Institute is not a scientific organization. It's a sort of professional advocacy organization that lies. Yeah, they specialize in lies. And now that the fourth climate assessment is out for the USA, they've sent people, they've fanned out to the media all over the place. And there's a gal in one of the media outlets, and she says, well, I'm not a scientist, but I can tell you that the Earth is cooling. And it's like, it's black is white and up is down. And to say the Earth is cooling is just like, it's completely opposite of all the observations and the scientific consensus. It's just kind of crazy. So people are offering folks something, one more thing that they don't need to worry about. And many people will take that and, yeah, I'll accept that. I have enough to worry about. Or I'm confused by it. Climate and weather are confusing, and people turn away from things that are confusing. So all you have to do is confuse them. You don't have to come up with an alternative theory. And it's galling, and it's frustrating, and that's what we live in. It's an American thing. The Canadians have picked it up a little bit, the Australians, but it's an American thing. You go to other parts of the world and they don't have this. They accept it and are looking to what they're going to do about it. So don't sit for lies about this. Be respectful, but don't accept falsity. And I tell my students that, and if somebody says this is a big hoax or isn't true or it's all exaggerated, please challenge that, okay? Because there is kind of a battle of ideas going on here, and we need to engage that and not just shrug it off. So, and the last one of that is NASA. You like NASA? Who doesn't love NASA? Well, these guys sent a Juno probe to Jupiter, and it traveled 1.7 billion miles over 4.9 years. And they predicted when it was going to get there right after it took off, and it arrived within 1 second of the predicted time.
Wow.
NASA tends to get things right. And they just landed an 800-pound geotechnical robot on a planet that's spinning at 54,000, orbiting at 54,000 miles an hour. So,
No insight.
Yeah, go inside. It's just amazing. So NASA confirms that humans are causing the rapid warming that we observe all over the world. So if your brother-in-law says, I don't believe this, is that why you're smarter than NASA? How many robots have you landed on Mars?
Yeah.
So anyway, this is a very important concept, and you probably all know this, but this is the difference between weather and climate. And weather is highly variable and kind of bounces around in a particular envelope, of variability, and the climate change is what happens over a long period of time. And so it takes a while to discern climate change. And in fact, the warnings about climate change came 50 plus years ago. And then it took 30, 40, it took a few decades to actually say, yep, sure enough, this is happening, and to figure out why it's happening. Now what this graph doesn't show is a change in variability. And that's something we worry about. It's something we don't really get from the climate models. And detecting variability of variability is quite challenging. The physics of climate change suggests that this will happen. We don't see it unequivocally yet, but it will probably happen. It's one of the things that is uncertain about all this. And when you look at the predictions, it is important to understand the quality of the predictions and the differences between different types of predictions. And there's at least 4 key streams of uncertainty. First of all, we don't know how much greenhouse gas and aerosol is going to be emitted by humans in the next century. We just don't know if we'll get it together or we'll just continue with the carbon party and make things bad. So that is just unknowable. And we can be hopeful about it, or we can plan for the worst, but we don't know what it's going to be. And then there's changes in climate variability and extremes. Again, we don't really get these from the models. It's not something we can push out of science right now. But the physics of climate change shows that we'll probably get big changes in variability and big changes in extremes. We just can't quantify them at this point. There's always climate model errors, and then there's natural variability in the Earth system. So radiative physics of the atmosphere is complicated enough, but it's not that complicated compared to the overall Earth climate system is wildly complicated. And there's some things that we don't understand or can't predict very well, and maybe we'll never be able to predict. So long-lived oscillations like El Nino and the Pacific Decadal Oscillation, random climate wandering from butterfly-type effects, volcanic activity, and nonlinear tipping points. So it is worth noting that in the media there's a number of, you'll see a number of stories that say, well, the whole Earth is going to like tilt in the next 5 years and everything is going to shit. And that's very unlikely. Okay? Climate change is a slow, gradual process. So you don't need to worry about, 5 years from now, we're going to be living in an absolute climatic hellscape. That, very unlikely. However, there are these tipping points of nonlinear processes. We're very good with linear processes and predicting things from linear that are linear. But a lot of nonlinear processes and processes that we haven't seen before and we don't understand very well, like the breakup of the ice sheet in Antarctica, or the methane hydrates in the ocean, or the melting of the permafrost and the release of methane from that. And we don't know where these tipping points are. And there could very well be tipping points where everything changes very quickly. And so that's what keeps the climate scientists and maybe many of you up kind of at night worrying about what might happen. Unlikely we'll hit any of these tipping points in 5 years or even 20 years. But those tipping points are there, and we don't really know where they are, and we don't know how vigorous they're going to be. So that's there. So California. California has it bad. This is a map of groundwater depletion. But overall, California is not at all a refuge, not at all a great place for riding out climate change. We have a hot, dry summer. We're subject to very long, deep, dry droughts. Wildfire, we all know about that lately. We have very vulnerable, warm snow that can easily change to rain and melts easily. And we have tremendous population pressure in California. So California itself is not a refuge. And there's a fly in the ointment. And I'm sure you've thought about this, or this occurred to you when you read the abstract. It's like, yeah, well, what about sea level rise? And this has been in the news, and there's been a lot of work done on this in our area just recently. Some very, very good work. And so this is the fly in the ointment. Or maybe it's like velociraptor in the ointment. And we're coastal, and like all the coasts of the world, we're seeing the impact of this, and it's very serious. However, the way to adapt to this is to understand the vulnerability, and we're in great shape here because of the efforts of Alderon Laird and Jeff Anderson and a number of other HSU alumni. We're in really good shape here as far as understanding what will happen here, what's vulnerable, what's not, what could be lost, and how we might move ahead. I'm going to circle back around on this one after I develop the Refuge story and talk more about it, because the sea level rise is a passion of mine as well. So first of all, temperature. What about temperature? And this is really the big one. That's why they call it global warming. And here's the trend, or here's the data, the observational data for the land and ocean since 1850. And when you include the ocean, it's about 1 degree centigrade over that time period. And you can see this, I have a stick. Don't fall asleep, I have a stick. You can see this tremendous slope here. This is very rapid warming. And we know now that this is all, basically all anthropogenic. This is not natural warming. And then this is the land function. This is what's happened since 1750 in land temperature. And this is the 1.5 degrees centigrade. This is from the wonderful BerkeleyEarth.org, the Berkeley Earth Surface Temperature Project that Professor Muller and his daughter have been running. Really great. And he's a climate skeptic, but not the kind of skeptic that denies the science. Just the kind that says, you gotta prove it to me before I'll accept it. So I recommend him, even though he can piss you off sometimes. So here's North America observations. These are not modeled results, these are observations, these are data. So there's nothing ambiguous about this, or, you know, models do have a lot of uncertainty around them. There are a lot of different models that give you different results. These are not models, these are observational data. And this is the North America, this is California. And notice that the slope here is quite a bit less than the North American slope. And then we've done some interpolation, and here's for the Arcata, Eureka, Fortuna area. And notice this slope here. And it's even quite a lot less than California. And it turns out the reason California is less than North America is because the coastal area is included. And basically, the story, more than anything that I'm going to develop for you, has to do with coastal proximity. That we have a monstrous cold ocean right next to us here. And it makes a huge, huge difference. And we don't really expect that to change much. So here it is. North America is warming quickly, California less quickly, but it's because the coastal areas are highly buffered for temperature. And this is the current average summer temperature. And like, brr. We're doing a little warm in here, huh? Especially lately.
Great summer day today.
I like the idea of warming.
Today was warm. Warmer than summer.
And then we've got this crazy ass hot valley here.
Crazy ass.
And then here's the projections for 2090.
Yay.
I mean, this looks like it's on fire, doesn't it?
Might be.
And then, look, it's still cool out here, and it's still cool along the coast. But this is not where people live, for the most part.
I live there.
You know, you drive the coast of Northern California and Oregon, Washington, there's just these little towns. You know, Coos Bay. It's not San Francisco.
Arcata.
Yeah, Arcata.
What's the red?
Yeah, we can't.
Yeah, what's the numbers? 1 million
Okay,
degrees.
100,
Can I read
200,
that?
110, 120, 130. What's the top?
Can you interpolate? Yeah, you go from 90
I'm
to
sorry,
100.
I'll check that out at the break.
The yellow is 100.
It'll cost you beer to get that value.
I'll get you a warm one.
Or those 5s and 10s. War beer?
And so here's another
Oh, here we go.
graphic of the change. And then here's yet another. And so you see a coastal effect there?
Yay.
So when it's 4 degrees centigrade warmer in Salt Lake City, it maybe be something like a 0.5 degree centigrade warmer here. And that
Temperature's gonna be nice.
is a very, very distinct effect. And what about heat waves? Well, they should be minor and not of really high consequence here, because what passes for a heat wave here, you know, it's like 80 degrees, maybe.
70.
Or it's 75 and everybody's complaining about how hot it is. You know, and so if we have a heat wave because of climate change that goes up to 85, it's not going to be the kind of heat wave that kills people and that kind of thing. Whereas if you're ready and your peak summer temperature is 117 or 118, and that goes to 122, you won't even be able to drive on the roads, they'll be melted. And people will be dying from heat waves. So heat waves is a major public health threat, and it's a really big impact from climate change. We're already feeling that in a bunch of places, and it results in lots of deaths.
Fires.
Probably not a big deal here because of this huge temperature buffering effect that we have. And then we have a soil temperature regime that's called isomesic. And mesic kind of means sort of middle of the road. And the iso means it doesn't even change much. And the iso part means it doesn't change more than 5 degrees centigrade at 50 centimeters down. And so we have this very big flywheel buffer in our soil temperature. And that's a significant factor, and that's because we're near the coast. And then one of the things that's observed everywhere is that the greater the elevation, the greater the temperature change. And it's actually not well understood why this happens, but the observations can confirm this every way you look. And we have mountains, but they're relatively low on the coast. So we don't have the big high mountains that we have, say, in Trinity County or all through the Sierras and Tehachapi's and that. And so we won't see that tremendous warming effect that the high elevations have. Okay, so what about precipitation and drought? So overall, there'll be more precipitation, more rain, and maybe even more snow over the globe. But the spatial distribution of that differs greatly from place to place. And we know that for every degree rise, 1 degree centigrade rise in global average temperature, that the atmosphere holds 7% more water. Okay, that's a big number. And so were we to go up 3 degrees centigrade global average temperature, with a 3 times 7, I don't do it, 21. That's a lot, that's an enormous change. And that results in an overall increase in precipitation globally. And basically, changes in temperature are pretty easy relative to changes in precipitation. Precipitation is a complex process, it's a threshold process, it's hard to predict. And the projections for changes in precipitation are all over the place. And for any given place, in the middle latitudes, they tend to, even the sign of the change, don't agree between the models. The sign of the change in temperature, they all agree. But precipitation is hard. So you might have noticed that the weatherman is almost always right on temperature and often wrong on precipitation. They will even bet you that they'll be within 3 degrees on temperature because it's easy, but not on precip. It's much more difficult to predict.
As temperature rises and precip increases, cloud cover would also be expected to increase. So the models also model increased cloud cover globally?
Yes, clouds are difficult to model,
right,
and only the most recent models are tackling it. But they are a big factor, and they both warm and cool the atmosphere. But they are including clouds. It's probably one of the big bugaboos for climate models is the clouds. Yeah, but it's very dependent on temperature and moisture. So basically, our winter rainfall is projected. Now this is with a grain of salt because the projections are not very good. For more rain and a little less rain in the fall, about even in the summer, and a little let's see, about even in the spring, a little less, about even in the fall as well. A little less. So we may have a dry fall, dry spring according to this, but a wetter winter.
Where is this in the future?
This is a projected change. I'm sorry, it should show this is for 2100. Yeah. But you know, I could show you lots of precipitation projections, and none of them agree. So here's another one: the change in spring precipitation. Spring is a big deal because it's late in the season. It has something to do with fire season and plant stored water in that. But we see a little bit of a decrease in spring precipitation, and then all of the models do predict that the southwest of the U.S. Will be bad. We'll see much droughtier conditions. So it's a dry place that's getting drier, which is not good. But basically for us, it's very small change predicted. And then this is an important factor. This is for the Pacific Northwest from the Climate Impacts Group at University of Washington. But the same thing applies to us here. And when you look at the projected changes relative to the range of variability that you see, in temperature, we're in a whole new world, okay? Massive change from where we are now to where we expect to be. Whereas precipitation, even with the changes that we may expect, we're still well within the range of variability. And so the take home there is temperature matters, and temperatures, the projections are pretty good. Don't worry too much about precipitation and the projections of precipitation. Now, the thing you do need to worry about is snow changing to rain, and I'll get there. And here's another projection. This is the 30-year average projected for 2084, and you can see we're in the area where there's little, this is a little bit down, this is a little bit up. And when you're in this zone where it's a little bit this way or a little bit that way, it probably means there isn't going to be a lot of change, but it does mean that there may be some change in variability. But that's where we're at. We don't expect huge changes in precipitation. And then when rain or snow falls on a soil, it's fractionated into two basic parts. You can make more parts if you want, but basically into green water and blue water. And the green water is the water that's held in the soil reservoir against gravity, and is available for plant growth. And some of it kind of slowly drips out over time, over the summer. And then there's the blue water that is excess to the green water and feeds the streams and rivers and the runoff, basically. And these are very important concepts. In terms of drought, you can have a blue water drought without a green water drought. You can't really have a green water drought without a blue water drought. Okay? And this is some fractionation graphic that we use teaching foresters in India. And our proportions are probably more like half and half. It depends on how much rainfall it is, the kind of soils you have and whatnot. They're showing more green water than blue water here, but think of it as about half and half. And the green water, of course, does all this stuff in wetlands and forests and croplands, and basically it's the water that's held in the soil. It's a lot of water. And that's why we have forests and grasslands and plants that grow, is because of the green water. And then the blue water is the stuff that feeds the streams and the rivers and that. And basically, how much do we need to worry about drought here? And essentially, even in a dry year, we have enough water to fill up our soil reservoir. So our soils hold about 2 inches of water per foot. The rooting zone is maybe about 6 feet, and so we need about 12 inches of rainfall to fill the green water reservoir. And so even if we had 39 inches of rainfall in an average year, even if we had 30% of that, we would have enough to fill up the green water reservoir. Now we would have a severe blue water drought, and the streams would be going dry, and the fish would be gasping So the blue water story is not so good, but the green water story is, you know, you'd have to be a hell of a drought to really have a bad green water situation. And this explains why we didn't see a lot of forest damage in the extended drought that we had, 2011 to 2015. We didn't see, for example, redwoods dying from drought, whereas there was a lot of drought mortality in other parts of California.
Michael, does green water go into groundwater to some degree, or is it depends?
Well, the green water technically is never exported,
Okay.
and groundwater would be considered blue water.
Yeah.
Yeah. And here's another fly in the ointment. We can see serious blue water droughts in terms of aquatic ecosystems if we have a drought that's related to higher temperatures or increased climate variability, or just the kind of thing that simply happens in California. Long, extended, dry, crazy dry droughts. We could see a lot of impacts on our aquatic ecosystems. And so I don't want to characterize that as a refugious situation. This is something that can be pretty bad, and we saw it actually. We saw very low flows in our streams and rivers in the last few years, and it was really hard on the fish. So that can happen. And I don't want to treat that as a refuge situation. That's one of the areas where we would worry. And then snow. So this is, California is probably the most consequential area for this particular climate impact. And that is, as temperature rises, more of the precipitation comes as rain than as snow. And the snow that does come melts faster. So the snowpack is really at risk. And California has warm snow. You consider vulnerable snow. It is, except at the highest elevations, it's close to zero when it snows. So it's a little below zero when it snows, but not very much. It wouldn't have to heat up very much, and it turns into rain. And you know, if you go to Minnesota or Pennsylvania, that's cold snow and is much less vulnerable than the California snow. So it'd have to warm up a lot to turn Minnesota snow into rain, but it doesn't have to warm up much to turn California snow into rain. And this is the projections for, this is the soil water equivalent in April, snow water equivalent rather, how much water, total water is in the snowpack, and 2030, 2060, and 2090. And I can tell you, this is freaking out the water district managers. As many reservoirs as we have in California, still 3/4 of our water storage for the summertime drought period is in the form of snowpack. And it's going away very quickly. All we would have left by this projection from Scripps is the highest elevations in the southern Sierras. And so I heard somebody give a talk about climate change in California, and he said, there'll be less snow, that's all you need to know. And there's a truth to that. That really is a huge problem for California and our tremendous water demand that we have in the summertime when it doesn't rain or snow at all. And so this is a big deal. And what about snow here? Well, this is the recent snowpack just a week ago, and it doesn't snow here much. And when it does snow here, it doesn't last. We don't have much of a snowpack in our mountains. And some of our hydrographs on our larger rivers do have a blue water component that it comes from snowpack, but it doesn't really, it's not a big number. Not like a snow-dominated hydrograph. We have basically rainfall-dominated hydrographs, and there's a small snow component. And our water supply basically is not dependent on the snowpack. Whereas in a lot of California it is. You lose the snowpack and you lose your water supply. Unless you build more dams, and that's not popular anymore. And so we don't depend on snow for our aquatic ecosystems for the most part. You know, Bill Trush isn't here. I expect somebody to argue with me about this one. And some others as well, but basically we don't depend on snow here. We're not a snow region, we're a rain region. And that adds to our the story about this being a refuge here. And then there's various maps of where water availability for people in agriculture is going to be bad, and you notice not at all bad here. Terrible in the southwestern U.S., but not up here where we are. And then this is a map of California drying, basically a map of soil water and groundwater that's been sensed by satellites, by gravity anomaly from satellite measurements. It's amazing that we can do this, but we can. And they can show groundwater depletion during the drought period. Really, really interesting. And then let's break kind of halfway here, and I'll take a couple of questions, and then we'll have a break by beer, by sandwiches, and we'll reconvene in about 10 minutes, and we'll continue to develop this story. And we'll also circle back to sea level rise. These days, after having gone through just a hellish couple of years, with devastating losses that I think we weren't, many of us, including me, who's worked in forestry forever, weren't really aware could happen, or didn't really grok that you can lose whole towns, like Redding and Santa Rosa and Paradise and Magnolia, and all the other towns that haven't burned yet. So there's a lot of discussion about wildfire. There's going to be a lot of discussion in the coming year about wildfire. And when you talk about increasing heat levels, increasing temperature levels, obviously that would influence wildfire and its ability to get going and sustain and how it behaves. And how long our fire seasons will be, how severe the fires will be, how many fires we'll have, how much acreage is burned. And the picture is not rosy. And so the data clearly show that we're having more wildfires in recent decades, and they're bigger. Now, there are many influences on this besides temperature, so it's quite a complex story. But even with all these wildfires, it's interesting to note that only about 11% of the western U.S. has burned since 1950. And so the frequency and size has increased, but the amount that is burned isn't as much as you might think. And in this map, the private lands are purple, the public lands are not colored, and these orange areas are places that have burned since 1950. And it turns out it's a random distribution. So when we look at private lands versus public lands, there's no difference in fire occurrence. And so this thing that you hear a lot of people saying is like, we're having bad fires because we're not clear cutting the public lands anymore. That's bullshit. We're not raking. Really, it isn't supported by the data, it isn't supported by the physics, it isn't supported by the forestry. But there are some folks that sort of take advantage of a crisis and say things that they've always wanted to say.
You got a rake?
It just isn't true.
Got a rake? A rake?
A rake, yeah, right. It turns out the worst thing you can do for soil productivity is to rake the forest floor off. The absolute worst. The only thing we've really been able to figure out about long-term soil productivity, it's crazy hard to research, but if you remove the forest floor litter, you deprive the soil of its food and the ecosystem of a very important component of the forest, and you lose productivity. So raking is a super bad idea. In an ocean of bad ideas, this one is the one hit me the worst. Also for its ridiculousness, but anyway, this area shows the locations of repeated fires, the areas that have reburned since 1950. And it turns out a lot of areas that burn, they burn again. And a decade or two goes by, the vegetation regrows, and it just burns again. And We know that the fire in Santa Rosa happened before with almost the same footprint. And the fires, the campfire, burned almost very similar footprints in that same area. It happened to spare Paradise and Magalia and didn't this time. But these areas that burn tend to burn and reburn and reburn and reburn. And that's just some stuff about fire, but here's the projected increase in the number of very large fire weeks. That is a week where the conditions are such that you can support really large fires, where it's really dry, the humidity is very low, it tends to be windy, and this is a percentage increase, and you can see it's really bad. It's a really bad story. And a friend of mine, David Peterson, who's a great fire ecologist, says by 2050 we'll probably have something like 4x the amount of area burned because of increasing temperatures. So it's a terrible story, but here we are sitting pretty again. And I don't want to tell you we don't have fires here. We do have fires here. We can have fires here. We could have a devastating fire here, but it's not at all likely relative to these inland areas that are much, much hotter.
What does that mean in terms of greenhouse gas emissions? Because like all this stuff's burning.
Yeah.
I mean, is that built into
Yeah,
the models?
that's a positive feedback mechanism.
Right.
If it gets warmer, you have more fires, you have more carbon dioxide released, you have more warming, you have more fires. So there's this is why climate science is not just the radiative physics of the atmosphere, it's how this all plays out in the Earth climate, in the Earth system. And there are scores of positive and negative feedbacks. So there's more CO2, so plants grow faster. That's a negative feedback. And you go down, and a lot of those feedback mechanisms are not that well understood. There's a lot of research going on now to try to understand those, because you need that to properly anticipate what's going to happen. But anyway, the projected increase in fires is bad, and we should worry about that, and it will increase in California, but really not so much here. What about flooding and storm surge? So basically, we don't get hurricanes and tropical storms here. And this is where the flooding is really bad, and especially the coastal flooding. And you may have heard that in Superstorm Sandy that hit New York, there was a storm surge of like 12, 13 feet. It was huge, enormous storm surge. Well, the storm surges we see here are like a foot or two, if that. And it's because we don't have those tropical storms that have this very long reach of wind blowing and push the ocean up like crazy. And so we don't have really bad storm surge. We don't have these big tropical storms. And steeper coast as well. And there is an expectation that there'll be additional atmospheric river-type storms. Large flood-producing storms will probably increase in most places, and will increase here. And so that is not a place where we think, oh, we're not having that either. You know, we will have that, but it is something that tends to happen in the valley bottoms. And we can and ought to deal with it with good land use planning and zoning. And we're sort of on top of that.
Vote!
Yeah, how many think we're all on top of flood zoning? Here's the prediction for tropical storm increases. So the models and the observations basically show that we're not having more hurricanes, but the largest hurricanes get larger. So the really destructive Category 5 hurricanes will become more frequent, even though the total number of hurricanes doesn't look like it will, or not in the next few decades anyway. But it's really the big ones that we worry about and cause the most destruction, obviously. And you can see there's an increase, late 21st century, and this is present day. There's an increase in the southern eastern Pacific, but it doesn't make it up into California. And so there's a lot of worry globally about the increase in these storms, warmer ocean temperatures, more energy, bigger shit-kicking storms, but not here. And the Gulf Coast, obviously, and the east coast of the U.S. is where the water is really warm. You have these hurricane cyclonic systems, and they're super vulnerable to these kinds of storms. And so it's worse there by far than here. And so what about fog? I know you all love fog so much, that's why we live here.
More fog!
We're fogophiles.
More fog!
We love fog.
We love fog.
Don't prejudice it, we have are fogophiles.
Mushroom. Fog.
It's a complicated process, okay? And I'm going out on a limb a little bit. I don't think much, but basically saying we can expect more fog here.
Yay!
Isn't that fabulous?
Colder summers.
Yay!
Isn't that great? And there were a couple papers published.
But not so far. The last 20
Seems
years.
nicer.
When less and less.
Yeah.
It depends on the data set you look at, and 2 summers ago was the most fog we've ever observed. It's highly variable, and people think there's less fog. And there were a couple papers written, and there was a big publicity thing that went with them. And you know, sometimes science by press release is problematic. And their conclusions about there being less fog from climate change, I was confused by the paper, and I thought that their argument was really thin. And they never looked at smoke. The word smoke never even occurred in these 2 papers, and there was an enormous amount of smoke generated here. There was a time when you could stand at the top of 11th Street and see 75 teepee burners that were going 24/7. And they were burning the clear-cut units. And it smoke, 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 smoke. And the smoke looks like fog and probably can even produce fog. And then, and then the smoke went away. Basically, the old growth party was over, and the mills kind of collapsed into a very small number of mills, and no smoke. Very, very huge decline in smoke. And so I think that's a real factor. And but when you look at what drives fog, basically the ocean gets really cold here in the summer because of strong westerlies that develop because of the hot inland area and the cold ocean, and this produces an uprolling effect where the cold water comes from the down in the depths and makes a very cold surface. And if you're a surfer, you know it's butt cold in the summer. It's butt cold all the time, but it's especially cold in the summertime. And the differential between the coast temperature and the inland temperature is what drives the movement of the marine air in and basically brings our fog. And so you probably noticed the hotter it is in Redding, the more fog we'll tend to have here. And that's really that driver, is that temperature difference. And that temperature difference is intensifying. And so it'll get hotter faster in Redding than it will here, and that should drive more fog.
Which would also drive more upwelling and potentially coastal productivity, marine environment.
Maybe.
Hopefully.
The ocean's a complicated place.
Right, very complicated.
Yeah.
Okay.
And fog is a complicated phenomenon. This might be wrong. And it turns out there's some people from USGS and a number of others that are really trying to dial down this fog issue. And so the conclusion isn't in. But my conclusion, and Troy Nicolini, the meteorologist at the National Weather Service here, agrees with me. He says, yeah, I think you're right, there'll be more fog because of this basic mechanism. And then it turns out, well, what if the ocean warms and then that differential will lessen? And it turns out the ocean's been cooling offshore here. It's a mystery, but for the last 30 years, it's actually been getting cooler. So,
What about the blob?
yeah, so that's the variability from year to year, and these are long-term trends. So, but there are things like the blob and a lot of things that we don't understand about the system. that could throw my conclusions and everybody else's into a cap.
It's a high pressure ridge.
And I just threw this in. This is the third national assessment of the United States projected changes in tick habitat. One thing we love more than fog is ticks. This is a real bummer for Lyme's disease and the other things that develop. And it's also true that the warmer temperatures are bringing in the mosquito that carries Zika and chikungunya and other nasty diseases into Florida, which we never had in the U.S. before, but now we do. So,
Florida deserves it.
And I'd like to address this question of redwood survival. And I am going out on a limb here, and I'm out of and I'm super nervous about it. Marie Antoine and Lucy Vergillis are right here.
Is it about the redwood bark beetle?
A couple of trees died from redwood, or were dying from redwood bark beetle in Redwood Park.
They're projected to die in 120 years.
But basically, redwoods are so bomber they don't have much problem with insects. But here's my take on this, and others may have a different take. This is the most famous and arguably the most valued tree on earth. Anywhere I go in the world, I say, oh, from where the redwoods are. Oh, you're from the redwoods. Yeah, people know the redwoods the world over. It's amazing. And they're so valuable, and we don't want to take any kind of a chance with them. But we say, well, there's going to be less fog, therefore we're going to lose the redwoods. Well, probably not. There's probably going to be more fog. And from everything I can see, many years, redwoods basically need fog for their seedling survival. Their seedlings are really vulnerable to drought. They don't grow roots very fast, and they perish if they don't have good summer moisture. And so their range, their natural range, is controlled by fog. And that's where we only find them in areas that are very foggy on the coast. But if that range starts to contract, we can very easily do artificial regeneration. We know how to do that now with planting seedlings or irrigating and whatnot. In terms of the survival of the mature forest, it's not essential to have fog. It will survive okay without fog. I'm sure you've seen redwoods in Sacramento where it's like crazy hot and gets really hot in the summer. And they can be just fine without fog, but they can't reproduce well by seedling without fog. And so that's the critical thing. And like I say, we'll probably get more fog. The redwoods have been here on the coast for at least 1 million years. And this is a hunch from Bob Van Pelt and others. But it seems very likely that they've been here for at least 1 million years and probably much longer. There are 200-million-year-old species. They used to be distributed all over the place. There was just recently a seed of coast redwood found in Redding that was 80+ million years old. And so they're a very old vegetation type. And the place where they would persist, even in times of very poor moisture, very low fog, very high temperatures, would be on the coast here. And we haven't been glaciated here. And we go up to Washington, and those forests were completely, the northern Washington were completely wiped out, and the Sierras were completely wiped out by glaciers. That didn't happen here. So we have a very, very old forest here. And if it's been here 1 million years, it's been through lots of different climates and lots of stressful climates, and it's still here. So that's a cool thing. Steve Norman is a great vegetation ecologist and did a lot of work in redwood. He's in North Carolina now, but he said, I guess I'd have to say this is one of the last species we worry about. There's a lot of forest species we worry about, but maybe not so much redwood. And we don't see indications of big impacts so far. But we don't want to take any chance with these. And the studies that we're doing with Humboldt State and, say, the Redwoods League are very worthwhile and ongoing. So there's not to say we don't have anything to worry about with the redwoods. But if somebody comes along and says, climate change is going to wipe out the redwoods. Probably not true. I have to add a caveat though, and this is true about like almost all of these impacts, that if we go to 2, 3, even 4 degrees centigrade increase in global average temperature, a lot of these conclusions will hold. If it goes above that, we go to 5, 6, 7, 8, all bets are off.
Yeah.
Okay? It turns into a complete shit show.
What about the,
Humanity must avoid these 8 degrees, for example, or we just lose the Earth. Probably the redwoods too.
what about the raven bark beetle? I've never heard of it before.
I didn't either. There is a redwood bark beetle, and
Is it gonna, expand if we get hotter?
these particular trees were covered with pavement and had ponded water most of the year, so.
Yeah.
Yeah, I think that's the
weakened.
bark beetle.
Weakened.
Huh?
I think that's the bark beetle.
Yeah.
The bark beetle is the pavement and the water.
Right,
Yeah.
Yeah, and then the beetles just kind of got in there opportunistically.
if they exist.
It's, redwood doesn't really have an insect problem.
I've never heard of it.
Most trees have an insect problem. Most trees have an insect or 5 that specialize in them and are really hard on them, and not redwood.
Right.
Yeah. So anyway, I really wanted to show up with some good news about this because it's, as you say, it's an unrelenting bummer. And there is some good news for those of us who live here about the refuge quality of our area, and that I believe, and we can have debates about this, and the studies. I'm so happy that those are going on because we want to take no chances with this amazing forest and species. And then it may be a different story with the Sierra and the giant redwood in the Sierras. It is a much different story because it's a much different set of climatic impacts. And I don't have a conclusion about that, but somebody might. So let's go to sea level rise. And this has been a passion of mine. I've been a coastal guy for a long time. And I've worked in Southeast Asia where the impacts are insanely bad and are already manifesting in some really bad ways. And then what happened here, and this is an indication of what a cool place we live in, some really bright people stepped up and figured out the land level elevation changes, the vertical changes in land, which we had to know, and the vulnerability of Humboldt Bay area. And so the first thing you do to adapt to climate change is a vulnerability assessment. And what's vulnerable, what's resilient, how can you change things that are vulnerable to be resilient? It's a knowledge exercise, and we've done that here. And we've done it as well as I've seen anywhere. So I thought Alderon would be here, but I don't think he made it. But Alderon Laird and Jeff Anderson. Are really preeminent guys in figuring this out, and it's all been published. And there's lots of, there's one for the city of Eureka, there's one for the city of Arcata, there's another one for Humboldt County. I put in so on here because I couldn't put them all in there. Jeff has done some amazing, he's just a really amazing, solid environmental engineer, done some great modeling of how Humboldt Bay works and whatnot. The environmental engineering resource department at Humboldt State does a lot of work on this. And so their capstone projects and senior projects and whatnot, they often take on the issue of sea level rise and have produced some really great work in terms of the impacts and how we might adapt. And so we're really in good shape in terms of understanding these impacts. And I wanted to go into just a little bit of detail about how sea level works for you that maybe you should know. So normally sea level changes quite radically through time as we shift from glacial periods to the interglacial periods. And the last ice maximum was about 22,000 years ago. And since then, sea level's been rising really fast with some especially fast pulses that were related to rapid melting of the ice sheets. And then about 7,000 years ago, it just stopped. And we've had essentially, there's been some small changes, but we've basically had stable sea level for 7,000 years. And that's what we think is normal. It's not actually. Normally, much more commonly, the Earth is, sea level is either rising or falling quickly. But we've had this 7,000 year period, and it probably enabled civilization to develop. Because you could have coastal cities, and you want your city to be coastal. It has navigation and food and mild climate, etc. Didn't have to keep getting up and moving. So during this period, that's when there wasn't an Atlantis. There must have been many, many Atlantics that set themselves up on the coast and then got inundated, and then moved, and then got inundated and moved. This is probably also the origin of the flood myths. But we think that we have a stable sea level, and that's basically over now. So the sea level rise is basically on about this kind of a slope now. And you could spend a whole college career on this one graph, but I'm going to move on. So this is what sea level looks like. So 20,000 years ago, it was 120 meters lower. And the beach was another 10 kilometers offshore. So we had a bunch, actually, a 10-kilometer strip of redwood forest that's now gone, it's under mud. This is the present sea level. And then if all the ice melts, you get about this much more. There's that much ice locked up in Antarctica and Greenland. It's actually 57 meters in Antarctica and 7 meters in Greenland. So Antarctica is really the big story. And we don't know how that will behave with rapid warming, but there's still a lot of water left on the continents that isn't in the ocean yet. And just a quick primer on how sea level rise works. First of all, there's thermal expansion. As the water gets warmer, it takes up more space, and so sea level rises. And then the melting and collapse of this terrestrial ice so adds water to the system, and sea level rises. But the other big part of the story is that the land level is not stable in most places, and it sure as hell isn't stable here. And we have things like isostasy, where there's a buoyant effect that can cause land to rise or fall. There's tectonics, which is the big story here, sediment, land subsidence, which is a big story in many parts of the world, and so on. And this can go up or down. And then you have things like El Nino, tides, storm surge, onshore currents, oh, that one's white, and wave height. And that all kind of goes together to sort of a complex picture of how local sea level works. But what you have to know in order to figure out the local, or what's called the relative sea level, is what's happening to the land level. And this was recognized, and there's also freshwater flooding that comes on top of that. So this is when you get the perfect storm, is when the tides and the storm surge and the wave height all come together, and there's flooding as well. So it turns out, as you all know, we're on the Ring of Fire here, and we are a seismic area. All these areas are seismic and have tectonic movements that are going on all the time. And these are where the earthquakes happen. And this is a graphic I got from Jay here about what's happening. He could explain it better than me, but I guess this is my lecture. So. But the Pacific plate is always moving under the continental plate here. It never stops at about the speed of a fingernail growing. But most of the time it's stuck. And because it's moving and stuck, that this land either goes up or down. It gets dragged down or it bulges up. And this is between earthquakes. And then when the earthquake happens, it moves all of a sudden, and again, it can go up or down when the earthquake happens. And we're sitting right here. Lovely. It's not a refuge It's not a seismic refuge, folks. I need to tell you. And Jay Patton is right here, and he had the foresight to put a group together, a vertical reference working group, I think it was called, or something like that, to figure out, is the land going up or down in our area, which is essential to know to figure out sea level rise vulnerability. And this is what they have come up with after all sorts of painstaking measurements. And it turns out on most of the coastal areas that are on the Ring of Fire, there's a rapid uplift and a net uplift and steep coasts. But the velociraptor in the ointment here is that that's not true of the Humboldt Bay area, which is sinking, and sinking fast. Can you feel it? Yeah. We're sinking here, and we're sinking at 3 to 5 millimeters per year, about the same rate as global average sea level rise. And so that doubles the effective sea level rise. And this is kind of the worst situation in all of California. Yeah. So, I know, I tell you, there's got to be a bummer. I have to fulfill my I will try and moderate this a little bit for you in the next few slides. Basically, where it's green, it's rising. That's cool. And all the way up Crescent City, it's rising. And so it's moving away from sea level and ameliorating sea level. But where it's falling, it exacerbates sea level. And too bad, but that's happening around Humboldt Bay.
Each of the bays.
You will
Yeah.
the whole
The whole area is sinking.
You're probably okay too. I'm definitely okay. I plan to.
And then here's something else that doesn't really have to do with climate change as far as we know, but you should know this, that you can get sea level rise, the kind of sea level rise that we worry about happening in 50 or 100 years, you can get that in like 2 minutes. Because of rapid subsidence during a big earthquake. And Lori Dangler tells me that during the big megathrust earthquakes, subsidence is common. So you can get rise, say in the big Anchorage earthquake, a lot of stuff jumped up, like between 3 and 10 meters. But this was the 2011 earthquake in Japan, and it sank. And these areas were not full of water before the earthquake, and now they are. So be ready for a large earthquake. They do happen here, they will happen here. It might happen in the next second. Oh, good. More beer. Again. Fantastic.
Life is good.
Let's drink beer.
Life is good. Yeah, probably won't even happen tomorrow. It might not even happen for the rest of your life. But you could wake up tomorrow and there's a whole new world here. And be ready for that. And what's going to happen to your house and you and your family if a big megathrust earthquake happens here while you're alive. It will happen. So just wanted to kind of throw that in. We are not a seismic refuge.
Jay likes that one.
Yeah.
A t-shirt. I'm going to make a t-shirt.
Mirror of the world. If you go to the East Coast or the Gulf Coast, you have very gentle slopes on the shoreline. And you may get a foot of sea level rise and 300 feet of incursion of the water into the landscape because of that gentle slope. But if you have a steep slope, like we have in most places here, not Humboldt Bay, unfortunately, but you have very, very much less incursion of the water into the landscape. And so having that steep coast that we have here is a benefit in terms of sea level rise. But is that vulnerable?
Yep.
This is out on the West Coast, so this is vulnerable. If sea level rises, this will probably erode a lot faster, but nobody lives there, unfortunately.
Yeah, one guy does.
Yeah, Thomas lives there.
One guy.
And then sea level rise is not homogeneous across the globe. You might think it's like a big bathtub. It's not. There's all sorts of heterogeneity. And we're actually seeing less global sea level rise here than in a number of other places because of bathymetry, salinity, the centrifugal effect of the Earth, the currents, and a whole bunch of other factors. But we're a little bit better off here on the West Coast. And then Alderon has shown that most of the Humboldt Bay is artificial shoreline. It's dikes or roads or railroads or something like that. And many of them are already failing. They're 100 years old, give or take, and nobody's really in charge of them. They're on private land. There's no dike district that kind of looks after these or looks after what happens when they fail. And they're actively failing now. So when you get a really big tide, and there's a number of failure points. And I'm not going to go into detail about the impacts of sea level rise here, even though I know that's interesting to people. But as I said, this has been dialed now, and there's a number of publications that are available that really show that for you. If you're interested, just go to the Harbor District website, or there's a Humboldt State working group on sea level rise, and all those publications are available. So you can pull those and see all sorts of maps about what the impact will be. But this is some modeling that Jeff Anderson did, and this is the 100-year high water, so an especially high tide, and maybe some inflow of flush water into the bay, although the bay doesn't have a big catchment area, and then 2 meters of sea level rise. And then
it's red.
Basically, this is the blue is the area that with the 100-year flooding, and the red is the increase that happens. And so there's special impacts on the shoreline of Eureka and the bottoms of Arcata and a number of other places. And this maybe isn't the best map to show, but basically there's a lot of stuff in the way, and especially infrastructure, and roads, utility lines, water lines, gas lines, sewage treatment plants, but not a lot of people live there. And so that's a kind of a built-in resilience, is that we didn't build out our sea level rise zone. It's also the tsunami zone, actually. It's kind of good that we didn't build there, too. But basically, there's a bunch of places in the world where that's not true, where it's full of people and farms and infrastructure and whatnot. And so we're maybe a little better off than a lot of places that heavily developed these coastal areas that are now so susceptible to sea level rise. And this is a frequency diagram. This may be a little confusing to some of you, but hydrologists live and breathe for these things. And so the current 100-year return interval is this value here, which with just a half a meter of sea level rise becomes like the annual level. So the recurrence interval changes drastically very quickly. And then when you get more sea level rise than that, the current 100-year level is exceeded anyway. So. And then if all the ice melts, which nobody knows if that's going to happen. If it does happen, we'll all be long dead. But it's not a great story for here. So Blondies is underwater. Yeah, I know, bummer. So have a beer while you can. Before the Antarctic is gone. And I think the top of Founders Hall would be sticking out of the water.
Yes.
So, yeah. And then here's the southern end.
Wow. Really? Wait a minute. Where are we?
But that's if all the ice melts, okay? And that could happen. You don't know. no historic evidence of missing ice sheets, and what the sea level was doing there looks really reliable. And so we don't know if that's going to happen, but it could happen. We have runaway climate change, and we don't get a handle on this problem, then that is sort of the end point, or the worst case situation of all the ice melts on the two giant continental ice sheets, and the impact. Arcata is gone, basically. Sunny Gray's gone.
What's the elevation?
300.
What was it? It was
64 meters.
You had it there.
64 meters.
If only we could go backwards in time.
212 feet.
212 feet. Sorry, it's not in meters, but
It was 64 meters.
64 meters.
Yeah.
There we go.
That's what's
But here's an interestingly good story about this, is if we will resist the urge to just dike it off. You can dike off, you can live below sea level. You know, 60% of the Netherlands is below sea level. Most of, all of Amsterdam is at least a meter or two below sea level. The Dutch have figured this out, figured out how to do it. And you can do it if you have money. A lot of money.
A lot of money. So you're using money to make it.
And there is sort of a knee-jerk response of, we'll just dike this off. There's going to be a bunch of places in the world where that's what they'll have to do, or they'll have to move. But with Humboldt Bay, if you allow the dikes to fail, and you don't build new dikes, the bay will occupy the footprint that it used to occupy, and you'll have a lot better habitat for fish and wildlife. Okay, the habitat increase will be quite substantial.
Yeah, it's a good thing.
And so, you know, we're reckoning that now, and with these vulnerability assessments and the press that has followed that, there's a lot of discussion in city councils and planning groups, in the Sea Grant group, in county meetings and whatnot about sea level rise. And we're sort of reckoning what we're going to do about it. And I would strongly advocate, let the bay go. Don't dike it off, except where you have to. And there will be those places where you have to. We're going to have to dike off the Arcata Marsh, for example. But otherwise, just let the bay do what it wants to do, and we'll actually have quite a benefit for fish and wildlife habitat. And if the Arcata bottoms floods from sea level rise and turns to salt water, you lose like 500 acres of pasture land, but you'll gain a whole bunch of freshwater coastal wetland, which is some of the most valuable habitat there is for migratory birds and for salmonids and for a whole host of other organisms. And so we have a choice here to try to fight it, and we know how to do it. And just go see the Dutch and they'll show you how to do it. And they needed to do it, you know. But if we let it go, let the bay go, we'll get a lot of benefit from that. And that's true in a lot of other places where you don't have a lot of infrastructure. Or say the Mackenzie Delta in Alaska, well, almost nobody lives there, and it's going to grow, and you'll get more salmon, basically, which is a cool thing. And just in a relative way, the sea level rise risks in the Gulf Coast and the East Coast of the U.S. And along the East Coast of Mexico and Latin America are much, much greater than they are here. And we have this Humboldt Bay problem, but overall in the western U.S., it's vastly less of a problem than it is in the eastern U.S. and the Gulf states. And then I'm very fond of working in Vietnam. If you haven't been to Vietnam, I really recommend. It's a wonderful place to go. This is Can Tho, which is the primary city in the Mekong Delta, at the very southern end of Vietnam. And it's a Holocene Delta, like all these other coastal features, Humboldt Bay, and the Nile Delta, and on, all developed in the last few thousand years during that stable sea level run period. This is what happens in Can Tho every time the tide gets high. And this is not rainwater, this is water from the Mekong River that just backs up in the sewers and comes into the streets. And they just live with it, you know, no big deal. But this shows you what a dire situation they're in. And so I have a number of colleagues there and have been working there, and this is what happens in the Mekong Delta with about 1 meter of sea level rise. This area is about 18% of Vietnam. It's about the size of 2 New Jerseys, but way over half the food, half the rice and half the fish comes from here. It's this incredibly fertile area, and 20 million people live there. And they're on a prosperity roll, so they're building stuff all over the place as this happens. It's an amazing thing. And to add to that, they have subsidence rates that are 5 times the rate of sea level rise in a bunch of areas. And what happens is that the groundwater turns salty. And so, or the surface water turns salty rather. The groundwater turns salty later. But the surface water turns salty, and so people dig groundwater wells to still get fresh water. There's a lot of fresh water and geologic fresh water. And they pull the groundwater out, and that causes the ground to sink more. There's more subsidence, and it's a negative feedback loop. So you pump the groundwater, the ground drops, the salt comes in further, you pump more groundwater. And then the whole delta is now losing sediment. It used to be a gaining delta that was replenished by sediments. Now with the dams on the Mekong, it's losing, doesn't have enough sediment to replenish itself. The salt is coming in about 10 times further in the summertime than it used to. So it used to come in 10 kilometers from the South Sea or the South China Sea. Now it comes in 100 kilometers. And it just changes everything. The Vietnamese people are very adaptable, but boy, are they going to have to adapt here. And then this is the salinization of surface waters. And during El Nino events, they have a reliable drought in Southeast Asia. So the water gets warm in South America, it gets cold in Southeast Asia. The Western Pacific gets cold, and that leads to a reliable drought situation. Well, they had a really bad drought 2 years ago, and the salt came way in, and it was a disaster, a real crisis situation. Not just for the Mekong Delta, but for the Red River Delta, and for Da Nang and Hue, and a number of other cities that are coastal and are subject to this impact. And the people there live right next to the water. And you can't believe that they do it, but they just kind of live with loss. They know how to adapt when they get flooded out. Where's this? Nile. That's the Nile River. The Nile is not just a river. Anyway, most of the people live along the river or in the Nile Delta, and it's highly vulnerable. With one, here's the sea level rise picture. Even half a meter of sea level rise in Alexandria is underwater. And Cairo's way up at the top here, so it's okay, but this whole end of the Nile Delta is highly vulnerable to sea level rise. And there's a bunch of other places, Bangladesh, there's a whole bunch of cities in India, cities in China, the Mississippi Delta, of course, on and on and on and on. This impact plays itself out all over the world. And in these low elevation, flat, recent, close to sea level areas is a place where people like to live. And it forms fertile agricultural soils, and it's where the farms are. And those big mega deltas of the world are where the worst impacts are. And it's almost immeasurably worse than what we're going to face here. So it's just like, yeah, you could be in a worse situation. You could be living in the Mekong Delta. Anyway, in San Francisco, the situation in San Francisco is not good. I don't think they have the same kind of subsidence we do, although I don't know. Do you know, Jay?
No, they don't.
But they have there's a big mega delta here.
That's subsiding.
It's not a coastal mega delta, it's inland because of the way California is set up. But this whole area is highly subject to sea level rise, including Sacramento. Sacramento is basically there because of a dike system. It's actually very close to sea level. And so this whole area is very vulnerable. More vulnerable than here in terms of the amount of area and and certainly in terms of the amount of people and value affected. And this happens already at high tide. This is the Embarcadero in San Francisco. We're already like right up against it in San Francisco. And here's an interesting thing. Most of the big tech firms are right down here in the innovation zone. So Google and Intuit, Facebook, even NASA's a little bit vulnerable, Cisco, Oracle, all of these big firms. Basically, when they went to build their big campuses, the valley was all built out, and so they went down to the mud flats and built them there. And so those places are all vulnerable. And you're probably going to see some diking.
They can afford it.
So,
They got money, they can move.
yeah, so Silicon Valley becomes like Amsterdam.
Lego.
Yeah.
They'll use Lego.
And then to close, I just wanted to mention the amazing sort of social capital, especially that we have here for adapting. And I think it's the reason a lot of us like to live here, is that there's amazing stuff goes on here, and amazing people. And Humboldt State is here. Fabulous. And we're rich. Now you might be thinking, well, I'm not rich. But you are. We live in a place where there's a lot of financial resources available when there's a public crisis. And resources in a way that you don't see in a lot of places in the world. For example, Vietnam doesn't have money like we do, even though we're not a rich county. You know, they don't have those same kinds of resources. And there's a number of other places in the world. Bangladesh doesn't have a government that can put billions of dollars into saving people from sea level rise. India doesn't, you know, and it goes on and on. So there's many examples, and it's a little risky to list them because there's many, many more than I've listed here, but we have the Schatz Energy Research Lab, which is an absolute world-class center for energy research, and they're all over the climate change mitigation situation and doing some amazing stuff. And of course, all sorts of stuff going on at HSU. Many of the tribes get it, and they take progressive action. They understand this problem, they certainly don't deny it, and there's a lot of progressive action being taken around it. I mentioned Alderon and Jeff and their vulnerability assessments. Steve Sillett and Ray Antoine and all in their Save the Redwoods League studies of the redwoods, super important. Marie's sitting right here. The Sea Grant Coastal Program, they had a big meeting and webinar this morning about offshore wind. Andrea Tuttle is a preeminent expert in forest carbon, and she's right here in Arcata, and goes to all the committee of parties meetings, and is really a very big player in forest carbon mitigation. Sharon Kramer with H.T. Harvey and Associates is a great expert in offshore processes and offshore wind, and is shepherding this process along, and so on. We also have a lot of forest carbon sequestration going on. Actually, Andrea and the, it's a nonprofit that she works with. Pacific Forest Trust. Thank you. I have the noun hole, and you just can't pull up those proper nouns anymore. Pacific Forest Trust. And Andrea and the Pacific Forest Trust were instrumental in getting the idea of a forest carbon offset accepted into the California cap and trade system. And now you can sell forest carbon, they basically rent forest carbon to the cap and trade system. And I'll just note that the cap and trade system is working in California. The whole world is watching this because we desperately need a market for carbon offsets, and it's working in California. And a year ago, forest carbon offsets were worth about $11 a ton. They're up to $15.05 a ton today. And there's expectation that when AB 31 is renewed next year, it'll be up to probably $25 a ton. And so it's a huge thing, and it's working. And there's a number of projects that are going on here. The city of Arcata jumped in really early and has already sold from the community forest over $150,000 worth of forest carbon offsets in the voluntary market. The Van Eck Forest is forest carbon offsets and is making a bunch of money on that. The Yurok tribe is doing forest carbon offsets. I think the Hoopa Valley tribe is also doing forest carbon offsets. No.
I don't know.
But anyway, the Yuroks are all over it. There's a big story in the New York Times about that, and so on. And then in terms of forest carbon offsets, redwood is really ideal. It's like insanely great because it grows fast, it doesn't rot, it doesn't burn. Everybody loves it. It's like the ideal carbon sequestration machine, you know, coast redwood. And, you know, a ton of forest carbon is a ton of forest carbon, but it's not really. A ton of redwood forest carbon is really great stuff. So, anyway, so that's working, and it's one of those things like, who knew electric cars would be so feasible already? And who knew that wind and solar power would be so feasible already? But they are. And who knew that we'd be selling forest carbon credits? That there would be a system of cashing in on a forest without cutting it down. Super cool. Yeah, but that's working. Yeah. And it's working worldwide. Yeah. And then here's an amazing thing. It turns out this is probably the best place on the West Coast to do offshore wind power. For a variety of reasons, one of which the military won't allow it in Southern California. But for a bunch of reasons, this is a great place to do offshore wind power, and the projects are developing very quickly, and it's likely that we'll have an array of offshore wind turbines in the semi-near future. So it's really, really cool. And the lights in this room would be from turbines, you know, 40 miles out at sea. Yeah, I know. And then there's a lot of things to work out before that happens, but I'm pretty confident that we'll work them all out.
I hope we can see them. There's fog. I hope we can see them.
So let's do a review here of the good news story that I'm trying to bring you today. First of all, the temperature is greatly moderated by our coastal proximity. The precipitation is enough, and there'll likely be more. The snow, where there is snow, there'll be less snow and more rain, but we don't really need it here like we need it in so many other places. Tropical storms, we don't have them here. Fog, there'll likely be more fog, so more moisture and cooler. The big windstorms like the Columbus Day storm, those are not expected to happen. That's not coming out of the models, and the high-end meteorologists say we don't think this is going to happen. It's likely that the redwoods will be okay. And then, of course, the yeah buts. We have sea level rise, we have flooding, we have some potential for blue water droughts. And then the bigger thing is, you know, we're a human family. There is a tremendous amount of suffering and loss and vulnerability across the globe. And just because it's good here doesn't mean we can relax and not worry about climate change. We have a human family, and there are a lot of people that are going to have it way, way worse than we do. That doesn't mean it doesn't have some damage here, or it's not a negative here, but it's way, way more negative in a lot of other places. And that's the kind of relative refuge story that I wanted to tell you. And I have a Vietnamese colleague who's studying in the Netherlands now, and she tossed this at me. And you remember the Think Global, Act Local? That was a big slogan back then. Well, she said you could flip that and it makes sense. And I won't tell you how it makes sense, but think about it. Okay, well, thanks for your attention.
Thank you, Mike.
Low battery, I made it.
Thanks a lot, Michael Furniss. And Michael said he's willing to stick around around. If anybody has questions, you can feel free to come up and talk to him directly. And thanks to Blondies again. And